Hi, in this video we will see the effect of adding up periodic signals, and we will do so with the help of several examples and illustrations. So the first example we are going to see is the sum of cosine waveforms. So what we have here is a cosine waveform. So this one is a cosine waveform which we can call as cosine 2 pi ft. It has a certain frequency, and we are going to add up several cosine waveforms of the same frequency and phase. That means they are perfectly aligned with each other and they have the same frequency as well. So we'll start with this first cosine wave, and to that we'll add a second cosine wave, which is this red waveform. And when we add these two waveforms together, so suppose we add these two together, the resultant of adding these two waveforms will be as the black waveform which we have obtained here. So what we notice is that the sum of two cosine waveforms is also a cosine waveform when the two cosines that were added were of the same frequency and phase. And then the green waveform is the addition of all three of these cosine waveforms. So when we added all three of them, we get this green waveform, which again is a cosine waveform. So the first thing we observe here is that the sum of periodic signals, cosine by the way is a periodic signal, so the sum of periodic signals is also a periodic signal. So the first observation we take note of is that the sum of periodic signals is also a periodic signal. So the sum of the first two cosine waveforms is also a cosine waveform, which again is periodic, and the sum of all three of those waveforms is again the green waveform, which is also a cosine waveform, which again is periodic. The next thing we need to observe here is when these periodic waveforms are added together, we note that since the added waveforms are in phase with each other, the resultant is an amplified version of the original amplitudes. That means the first two waveforms had a smaller amplitude. When we added them together, the amplitude of the sum is twice that of the first two waveforms, if you notice. So the signal, the sum is amplified means its amplitude is increased. Okay, amplitude increased when the waveforms being added are in phase, when the signals being added are in phase. So what do we mean by in phase? We mean that the waveforms have the same phase with respect to each other. So if you see all these waveforms, they have the same phase. That means they are perfectly aligned along the time axis. So that's the sum of cosine waveforms of the same frequency and phase. So we'll illustrate the same thing again with the help of a different example where we have the sum of sine waveforms of the same frequency and phase. So we have the first sine wave, to which we will add a second component. So that is say sine 2 pi ft, to which we add another sine wave of the same frequency, and that results in this waveform. And when we add all three of them together, so when we add all three together, that would lead us to another sine waveform, which is this one. So again we notice the same thing, that the sum of periodic signals is again periodic sum of periodic signals is also periodic. Okay, now let's take this a bit further, where we can have a combination of sine and cosine waveforms together. So when you have a sine wave and a cosine wave added together, so the first one here, this one is a cosine waveform. Cosine, you can call this cosine 2 pi ft, and this is a sine waveform of the same frequency, so that's sine 2 pi ft. And when we add these two together, we get a different waveform. But now if you observe this third waveform, so let me pause this for a moment. So this black waveform, which is a sum of the top waveform, which is the cosine wave, and the red one, which is the sine wave, is a sinusoid, but it has a phase shift. So if you look at this black waveform, it is a sinusoid, but it has a phase shift with a phase shift. And we should also remember that the sine and cosine have a phase shift of 90 degrees between them. So when we add these two waveforms, we get another sinusoid which has a phase shift which is neither 0 nor 90, but somewhere in between. And the amount of amplification that we get also will depend on the relative phase difference between the added waveforms. So if you notice, the purple waveform and the red waveform, they have a certain amplitude, but the added waveform, the black waveform, it's having an amplitude which is greater than the original two waveforms, but it also has a phase shift which is slightly different from the original two waveforms. So the it results in a sinusoid with a phase shift. But again, the concept that the sum of periodic signals is still periodic. So even though their phase may be different, because the cosine and the sine, okay, because the cosine and the sine are periodic, the resultant of adding those two is also periodic, albeit with some phase shift. Now when we add all the three waveforms together, so we get another waveform which is also periodic. So this is also a periodic waveform. So this is also periodic. So what we conclude again is that irrespective of the phase of the sinusoidal components or the other periodic components, the resultant will still be periodic. So sum of periodic waveforms or periodic signals, of arbitrary phase is still periodic. We need to remember, be careful about the arbitrary phase terminology here. Of course, if the phase is 180 degrees, the waveforms when added together will cancel out each other, but I'll go into the details of that in a separate video. But here we'll focus the case where they are not necessarily out of phase or 180 degrees, but have some arbitrary phase difference between them. So the resultant waveform when added is still periodic. So we want to highlight the fact that the sum will still be periodic. So we have illustrated here with the example of sine and cosine waveforms. Okay, so let's see another example. So where we have now the sinusoids or the periodic waveforms that are being added, they are of different frequencies. They are not of the same frequency. So the previous three examples that we saw, they had the waveforms that were added of the same frequency. But now we will choose waveforms which have a frequency different from each other. So the waveforms have different frequencies. So the first one here is, as you can see, is a cosine waveform. It's a cosine, so that's a cosine, and this is a sine waveform. But if you notice the time period of these waveforms, the sine waveform is having 2 cycles in the same time interval that the cosine is having 1 cycle. That means the frequency of the sine wave is twice that of the frequency of the cosine wave, and when we add these together we get a waveform which looks something like this. So this is the sum of the black waveform. This black waveform is the sum of the top 2 waveforms. So when we add this cosine plus sine, we end up with this. And then what we do is we add a subsequent waveform, one more waveform to this, and then we see the effect. The effect is something like this. So when we add all 3 together, we get this waveform. The point that we want to note here is that the resultant is still periodic. So if you look at this waveform, it is still periodic. So if you notice, it starts at a certain point here and it completes the a pattern in a certain duration of time. And so is the case with this green waveform. This is also periodic. Now, what is the period of the resultant waveform? If you notice, the black waveform as well as the green waveform complete one period or one repetition in the same interval as the longest period of the added waveform. So the longest period corresponds to the purple waveform at the top. That means the purple waveform has the lowest frequency. That means it has the longest time period. And the resultant of adding periodic signals is periodic, and its period will correspond to the largest period present in its constituents. So let's write here, when we have sum of periodic signals, of different frequencies or correspondingly different time periods is also a periodic signal, and the period will correspond to the largest period present in the constituents, and the period of the sum is the same as the largest period in the constituent waveforms. So in the constituent waveforms. So that means the largest period of all these waveforms is the top one, which is the violet waveform, which has the largest period and hence the smallest frequency. And when we add up these waveforms, the sum has the period which is the same as the largest period in the constituents. Okay, so now let's look at another example where we have just the cosines of different frequencies. So we have different frequencies of the signals, but without any phase shift. So we have this is a cosine wave, so this is also a cosine wave, but its frequency is twice that of the top cosine wave. And when we add them together, so when we add them, we get this waveform, which is periodic. And if you notice again, the period of this waveform, the sum, is the same as the period of the top waveform, which is the largest period at this point of time. And when we add a further component to this, we get another waveform. So this is also a periodic waveform when we add it. So we get another periodic waveform, and again the period of the green waveform and the black waveform is the same as the period of the purple waveform on top. So the sum of periodic signals produces another periodic signal, and the period of the sum waveform is the same as the largest period in the constituents that have been added together. Okay, so similarly we have another illustration here with the sine waveforms, where we have sine waves added together, but they are of different frequencies, and we again observe the same effect. So that's a sine wave, that's a sine wave also, but its frequency is twice that of the top sine wave. And when these two are added together, we get this black waveform, which is periodic with the period same as the purple waveform. And this is again periodic with the period same as the longest period in the signal. So when you add periodic signals, sum of periodic signals is periodic. Okay, and the period of the sum waveform is the same as the longest period present in the constituent waveforms. Okay, and we'll do one more example here just to illustrate and emphasize the concept. So we notice the same observation in all the cases. To summarize the concept of this the concept covered in this video, so the first thing we want to say is thus: when we add periodic signals, we get another periodic signal. So when we add periodic signals, the result is also periodic. Also periodic. The next observation or important point we take from this video is the sum waveform. The sum waveform may have a phase which is different from the which is different from the constituent waveforms, from its constituents. And the final takeaway is that the amplitude of the sum waveform, the sum will exhibit amplification provided the waveforms or the constituent signals are not out of phase. Provided the constituents are not out of phase. Okay, that means the waveforms or the constituents should not be 180 degrees apart of each other. If they're having a phase difference of 180, it will result in cancellation. So as long as they are not 180 degrees, the resultant would have some sort of amplification, and that depends on the amplitude and frequency and phase of the waveforms that are being added. To summarize, the sum of periodic signals is also going to be a periodic signal.